All right, good morning, class. This is lesson 9, covering section 2.2. We're going to talk about inverse matrices today. So remember, just to keep in mind things, if you look at the schedule on Canvas, you're going to see that we have a lecture today. Then we have a lecture tomorrow, the 18th. And then the 19th, we don't have any lecture. But instead, we're going to have a review for the midterm, right? So July 19th, that's this Wednesday. Instead of any lecture, all we're going to do that day is just kind of review all the past sections we've covered. So in order to have that kind of review session, I'm probably going to offer the review session to be 6 p.m. to 7 p.m. Eastern time zone, Wednesday evening. So I'll create a link, a Zoom link on Canvas for the midterm review that people can attend. That will also be recorded, and I'll make that recording available in case you're not able to attend them, but you still want to see what people talk about. With that being said, the problems are going to be very similar to the kind of homework problems, so you want to make sure you're reviewing the homework for practice. I'll also later today publish a list of suggested exercises from the textbook. Now those exercises, I'll be suggesting problems which are odd numbers in the textbook. The reason I'm doing that is because if you look in the back of your textbook, all of the odd numbered questions have their answers also written there. So you can use that to go back and look and say like, hey, are you understanding these sections? Well, if you're getting the right answer that matches the answer in the back of the textbook, then great, you can check for yourself and see, are you actually getting it or not? So do take advantage of that for extra practice. But Wednesday, when we do the review, that's all we're going to be talking about. We're going to be talking about those other suggested problems or any homework problems you guys want to talk about that maybe you found difficult for one reason or another. Midterm review is not required. If you, in fact, nobody has to come to it unless you want to if you're looking for help. There also won't be any participation question for Wednesday. So no grades, nothing will be due on Wednesday. It's purely just a day for practice and review to prepare for the midterm. Now, as far as the midterm, generally, when I ordinarily teach this class, the midterm is a timed test. Usually you would be given like an hour and 15 during a regular semester to take this test. Now, of course, I realize that this is online, asynchronous, so we don't really have a meet time or a class time where like we can have an enforced time limit with that regard. So instead, and I gotta look into Canvas, see how this can be done. But what I may do is I'll create a midterm assignment that once you open the assignment, a timer is already going to start, right? So you don't want to open the midterm until you're ready to actually do it. Again, do not open the midterm until you are actually ready to do it. And I'll make announcements about this on Canvas as well. But so in case you're a student who maybe you want to download the midterm and you want to print it off and you want to write it out for yourself, or you could also put it on a tablet or anything else, and you can write directly on the test for your tablet. That's fine. I really don't care how you do it, so long as, again, you're showing your work and, you know, not just writing down an answer with no work to back up that answer. Of course, I mean, there are some questions where like, you can tell by looking at it, like, oh, column 2 is a multiple of column 1, therefore linearly dependent, right? And that would be a valid answer. You wouldn't need to do any more work than that. But other questions where it's like, find the reduced echelon form of this matrix, well, you got to go through the steps of row reducing the matrix and showing your steps as you go. So that kind of thing I would expect shown work. Yes, it's true that there are calculators like the TI-83 or TI-84 that have matrix commands that can automatically reduce a matrix for you. making sure you've reduced the matrix correct yourself during the midterm. But you should not be using that as a way just to jump to the answer and just say calculator. That will not receive credit, right? After the midterm, so for like the final exam, it's fine if you just want to use your calculator instead of reducing by hand and just say, oh, here's the reduced matrix according to the calculator. That's fine. When we get to the final exam, I will not be expecting shown work for reduced matrices. But for the midterm, I do expect to see that shown work just because for a lot of the questions that we deal with and answer in linear algebra, it's important that you understand the process of row reduction because that's really the backbone behind how we get a lot of the answers that we have. So for midterm, shown work for reduced matrices will be required. For the final, not required. Okay, good. So, right, the midterm will be timed so that once you open the assignment, you will then have like an hour and a half. That will give you time to download it and print it off if you want. That also give you time that if you're doing this on paper, then you want to make sure you stop like 10, 15 minutes before the cutoff time. Take your pictures, scan it, upload. So you'll have to upload your completed test, your completed document of the test within that time window. So that's why I'll make it an hour and a half. Ordinarily, this test would be designed to be done in an hour and 15. Well, I want to give you 10 minutes before and after to like download it if you need or print it, and 10 minutes after to upload. So I'll probably give you like an hour and 40 then. An hour and 40 to download, complete it, and upload. So what that means is that it's also timed in that regard. So you can't just take all to do the midterm. Upload in time, it will be considered late, and tests are not accepted late. So you want to be very careful about that. You want to make sure you do submit it on time. So just be wary of that, right? I mean, you don't want to like miss it by 10, 15 minutes, and then you can't upload because the assignment is closed, then you get a 0 on the midterm. That would be really bad. So you want to really pay attention to the clock when you start. Make sure that you're uploading within that time window. But again, I'll have more information about this in an announcement that I'll post on Canvas later today. Okay, great. So for now, let's go ahead and jump into today's lecture. Again, this is lesson 9, section 2.2, and we're talking about inverse matrices today. All right, so what is an inverse matrix? Well, first of all, let's back up to some regular college algebra, right? If I give you, let's say, the equation little a times x equals 2, and this is just regular college algebra, regular high school algebra, forget about matrices for a moment. Well, for regular real numbers, you could just divide a over, right? And you could say, oh, x equals 2 over a, right? And you would have your answer. Okay. But for a matrix equation, we would like to find some kind of equivalent way of solving for x. So we have ax equals the vector b. Now we know, of course, from what we've done so far in the class, that we can solve this equation by taking the matrix A, augmenting with the vector b, row reduce, and then solve for each variable of x, right? We know we can do that. But what if A is like some big nasty matrix, like let's say A is a 20 by 25 or something like that, or a 30 by 30 matrix, right? 30 rows, 30 columns. Well, trying to reduce that matrix, especially if you're trying to reduce it by hand, that could take all day, right? I mean, that's going to be an awful kind of method to solve this kind of question. So we'd like to find a faster methodology for solving the matrix equation. Okay, well, if we think about the college algebra example, we would like to just divide the matrix A over, and then we would be done. We would say x equals b divided by a, right? Well, almost. The issue here is that we don't have any way to divide matrices in matrix algebra, right? We can multiply matrices, we can add matrices, I can multiply them by a scalar, but we don't have any way of dividing a matrix. So if I were to write A wrong, I've seen students here is a vector divided by a matrix, matrices, because we do not have division as an operation for matrix algebra, right? So never ever do this. Never divide by a matrix. You will get it wrong. You will be counted off and you will lose points, right? So don't do that. Some students are still going to do it despite this warning, but at least I've warned you now. Okay, so what can we do instead? Well, let's back up to regular algebra again, just algebra with real numbers. If I have 3 times x equals, let's say 2. We don't need to make it complicated, right? We know I can just divide 3 over, right? And that would work. However, what's another way of dividing by 3? When I divide the right side by 3, well, that's the same thing as multiplying by 1/3. Right? Dividing this whole thing by 3 is the same thing as multiplying by 1/3. Or in other words, I'm multiplying by 3 inverse. Right? So when I have 3 inverse or 3 reciprocal times 3, this is 1, right? Again, just regular high school algebra. And so when we do this, we end up with x on the left side and we get our final answer, right? Now for real numbers, yeah, having a fraction answer like this, perfectly fine. For matrices, again, we cannot divide matrices, right? This would be a matrix times a matrix, and then you would have some new matrix, right? You would never divide a matrix. So what's the equivalent here? Well, I also want to highlight, what is the number 1? The number 1 for the real number allocative, right? In other words, for any real number, if you take 3 times its reciprocal, 1/3, you're always going to end up with 1, the multiplicative identity. Well, the same thing is going to happen with matrix algebra, except instead of equaling 1, it's going to equal the multiplicative identity for matrices, which is the identity matrix, right? So now we have our definition. Let's write this out. We also want to note this is only going to work for square matrices. If your matrix is not square, you cannot find an inverse. And we'll talk a little bit about why in a moment. So let the matrix A be a square n by n matrix. Okay. We're going to say A is invertible, or in other words, an inverse exists. So we're going to see there are some cases when an inverse does not exist, right? So this is one thing that makes this is another example of what makes matrix algebra different from regular real number algebra. For real numbers, you can always find its inverse by just taking the reciprocal, right? But for matrices, we're going to find that, well, this reciprocal, the inverse of a matrix A, might not always exist. And so sometimes you might not be able to use the strategy of trying to find an A inverse. And we'll talk more about this. But we're going to say a matrix is invertible if there exists an n by n matrix C. So notice this matrix C, it has the same dimensions as the original matrix A. And we're going to see this is one reason we require that A be square. All right. Such that C times A is the identity matrix for an n by n, right? So we're asking that whatever C is, when we multiply it by A, it's going to result in the identity matrix. And we want to require that if we flip the order, that the same thing should still happen. Now, this is why we require that A must be square. Why? Well, let's just think about it for a moment. What would happen if A was not square? Well, if A was not square, let's say A is a 2 by 3. Okay, well, what's the matrix C? The matrix C, according to this definition, has the exact same dimensions. C is a 2 by 3, right? Well, in this case, I would not be able to calculate A times C, right? Because there would be a mismatch right here with the columns and rows. And we know for matrix multiplication, we have to have those numbers match. So we couldn't calculate it. Just as if I flip the order, C times A, well, we still couldn't calculate it, right? Okay. So this is one reason for why we're going to require that A must be a square matrix before we can talk about finding inverses, right? Okay. What else can we say about this matrix C? Well, C is called the inverse of A and is denoted A with a -1 power here. Now, I want to be clear about the notation here. A raised to this -1st power does not mean 1 over A, right? That is not what this notation means. A inverse here, you can think of this as like the same thing with functions, where you can have inverse functions. The inverse there, when you have an inverse function, well, this is not 1 over f, right? Same idea here. When I say A inverse, even though it has that -1 power, that does not mean it's 1 over A. A inverse does not equal 1 over A. Why? Because we can't divide by matrices, so 1 over A doesn't even make sense. Okay, good. So when we have this A inverse, then we have A inverse times times A is the identity matrix, and A times A inverse is the identity matrix. Now, why can I flip the order? Well, the same reason we can with real numbers. If I have 3 inverse times 3, well, that equals 1. But that's also 3 times 3 inverse. So inverses is one of the rare occasions when, for matrix multiplication, you can flip the order and get the same thing. Remember when we've talked about matrix multiplication before, you can't necessarily flip the order. Flipping the order of matrices are being multiplied might result in different outputs. So in general, for matrix multiplication, A times B does not necessarily equal B times A, right? And we've seen examples of that in the past sections. But when we're talking about an inverse matrix, that is one of these special cases when we can flip the order and it's going to be okay. All right, great. Well, now the question is, how are we supposed to find A inverse? How do we find the inverse matrix? Well, first, before we do that, let me just show you an example of how this works, or what this looks like in practice, and then we'll talk about how to find A inverse. So let's suppose A equals the matrix 2, 5, -3, -7. Now, matrix is, we're going to double check things work, and then we'll continue. But for now, I'm not telling you how we find A inverse. I'm just showing you an example of an A inverse. A inverse in this case is going to be -7, -5, 3, 2. All right. But does this actually work? Well, A times A inverse is 2, 5, -3, -7 times -7, -5, 3, 2. Okay, so let's do the dot product. Multiply across the row, down the column. 2 times -7 is a -14, plus 5 times 3 is 15. Well, 15 minus 14, 1. Okay, looks promising so far. Now I'm going to multiply across the first row, second column. 2 times -5 is -10. 5 times 2 is +10. They're going to cancel each other out. All right. Second row, first column. -3 times -7 is a +21. Plus -7 times 3 is a -21. We get 0. And then second row, second column. -3 times -5 is +15. +15. Plus -7 times 2 is a -14. We get 1 again. So great. This resulted in the identity matrix. So why do I like this? Well, if I have AX equals B, I can multiply on the left side by A inverse. Now, again, remember, order of multiplication with matrices, super key, right? So remember, I can't flip the order of A times X, right? Because X would be a 2 by 1. And if I flip the order, you can't compute it. So I can't flip the order here. So I have to multiply by A inverse on the left. A inverse, that would be wrong. You can't do that, right? Remember, for matrix multiplication, order matters. You can't just write it in whatever order you like, because it might be something that you can't even calculate, right? So the order in which you're multiplying things is super key, right? Now we know A inverse times A. Of course, this showed that A times A inverse is the identity, but you can also double check, well, what about A inverse times A? Do the same thing we just did, and you're going to get the identity matrix for a 2 by 2, right? So this is going to work. This will result in the identity matrix, not 1. Do not write number 1 here. That's wrong. It's the identity matrix. And the identity matrix times X, we know, because it's the identity, that's just X. So then X will equal whatever A inverse times B is. So we can use this as an alternate way to solve for X. Today's lecture, we're not really so worried about trying to do this yet. For today, we just want to get used to the inverse and get used to how to find the inverse, which we're going to talk about next. But in practice, this is how you can use the inverse to solve for a vector X. Okay, good. So great. A times A inverse is the identity. And if you want practice with the dot product, try multiplying it in the reverse order. If you do it correctly, you should also get the identity matrix. All right. That's all fine and good, but how do we find the identity matrix? I gave you an example of an identity matrix, but I haven't told you how to find it yet. Let's do that next. or inverse matrix. Okay, which works for 2x2 matrices. There are theorems and formulas for bigger matrices, how to find an inverse for a 3x3, a 4x4, a 5x5, so on and so forth. And that is something we're going to talk more about later. But for today, I just want to keep it simple. Let's just focus on finding the inverse of a 2x2 matrix. All right. So theorem. Suppose the matrix A is this 2x2, and it has the entries A, B, C, D. And we're going to have this specific requirement that if, and this requirement is key, if A times D minus B times C does not equal 0, why this specific equation? Well, we're going to see in a moment. Then A is invertible, and moreover, what is the inverse? A inverse is going to be this weird formula where on the outside of a matrix, we have to divide by AD minus BC, and then we're going to multiply it times the matrix where I'm going to flip the first diagonal, the left to right diagonal. I'm going to flip the diagonal. So I'm flipping A and D here. And then for the off diagonal, this is the diagonal from right left, the off for the same thing. For the off diagonal, instead of flipping the order, I'm going to flip the sign. I'm going to put a negative there. So negative B, negative C. And this is going to be our formula to find the inverse matrix for any 2x2, no matter what A, B, C, D are, so long as AD minus BC does not equal 0. Why do we require that it not equal 0? Well, look in our formula. I have to divide by AD minus BC. So if AD minus BC equaled 0, well, I'd be dividing by 0, and I can't do that. So for any 2x2 matrix where this turns out to be equal to 0, the inverse does not exist. Why is that? Well, we're going to talk more about that in a moment. But this AD minus BC, what is it? Well, I'm multiplying the first diagonal, and I'm subtracting what I get when I multiply the off diagonal, right? So multiply one diagonal minus multiply the other diagonal. That's what this is. That has to be not 0. All right. But why is this formula correct? Where is this coming from? Well, just as a little proof, as a little evidence for why this theorem is true, so you don't just have to believe it for no reason, let's actually try to figure out what the A inverse would be. So here I have a matrix A, B, C, D. I want to multiply it by an inverse, but I don't know what its inverse matrix is, right? So because this matrix is unknown, I don't know what I need to get the identity matrix. For now, I'm just going to call this E, F, G, and H. And because at this point, for the proof, I don't know. And also, let me put this in a box because this is really the key piece from part of the board. Okay, formula. I want to know, okay, what matrix, right? What does E, F, G, H have to be? I want to solve for E. I want to find out what does E have to be, okay? Well, if I do the dot product, I'm going to multiply across the row down the first column. I'm going to have A times E plus B times G equals 1. Now I'm going to do the same thing with row 2, column 1. Again, I'm trying to focus on column 1 here because I want to isolate E. I want to solve for E. All right, well, row 2, column 1, we have CE plus DG is supposed to equal 0. All right. Now remember A, B, C, D, E, F, G, H. These are lowercase letters. These are just real number constants, right? Okay. I want to solve for E. So actually, I want to replace G here. So I only have one unknown, right? Currently, A, B, C, and D, even though they're letters, these are known constants. They are whatever constants you're given in the matrix. It's the E, F, G, H, which are unknown, right? E and G are unknown. So I'm going to take the second equation and solve for G. So I'll have a negative CE divide by D. I get G equals negative CE divided by D. Okay. Well, now I'm going to take it and plug it into the first equation. So now I have A times E plus B times G, which I'm going to plug in now, is negative CE over D. And this is supposed to equal 1, according to the first equation. All right, well, now I only have one unknown, the letter E. So now I can solve for E and figure out, what does this first entry of the inverse matrix have to be? All right, well, I need to multiply here. So we have A, E minus B, C, E over D is supposed to equal 1. This fraction is kind of messy right now. So I'm going to multiply everything by D. So I have D A E minus B C E equals D. So I'm almost done. I'm trying to solve for E. So I'm going to factor out E, and I'm going to have A D minus B C. I'm just rewriting the order here because D numbers, D divided by AD minus BC. Or in other words, I can pull off that fraction and I get 1 over AD minus BC times D. Well, that's exactly what we have in the first entry for this inverse matrix. If I take this fraction on the outside, and this is just a scalar, right? This is just a constant scalar. 1 divided by a constant is still a constant. So when I multiply that scalar, my first entry is going to be D divided by AD minus BC. Well, that's exactly what we solved for when we did the dot product here. So great. If you then take this same strategy and do the same thing, solve for G, solve for F, solve for H, you're going to find out it's exactly this formula. For the sake of time, I'm not going to go through all of the steps for this proof, but I've shown you like how we get the letter E. Through the exact same process, you could get G, F, and H. In fact, these two equations I chose that I was trying to solve for E. But if instead you want to solve for G, well, then take the second equation, solve for E, and plug it into the first equation. Then you would have an equation with only an unknown of G, right? So you can use this methodology, and this will prove where this formula is coming from. This is why this formula works. It's also why AD minus BC has to be not 0. Because if it was, well, then I couldn't calculate this, right? Because I can't divide by 0. Okay, good. So we have this theorem now, and we can use this to find any 2 by 2 we like, the inverse for any 2 by 2. Now, before we do some other examples, I do want to highlight it real quick. What's special about this? More about this. I believe it's later in chapter 2. Maybe it's chapter 3. But later we're going to see that this AD minus BC actually has a special name, and this calculation is going to be very important, honestly, from here to the end of the summer session. And from here to the end of the summer, this is going to be a very special equation we have here. All right, so if A is a 2 by 2, so we're assuming A equals A, B, C, D, just like we have up here, then the determinant of A is, and oftentimes determinant is abbreviated as DET. And also sometimes in textbooks or in other textbooks, if you have different sources you're reading about, they either might do determinant parenthesis A, or they might drop the parentheses and just say determinant A. Either way, this is the same thing. And what is the determinant? The determinant is this calculation, AD minus BC. So put another way, this theorem says the inverse exists only if the determinant is not 0. What is the determinant? I mean, we see that it popped up in this formula when we did that proof just a moment ago. But what's so special about? What is it actually doing? That's going to be a topic for another day. For now, just put a pin in this, and we're going to come back and talk about determinants later, probably next week, honestly. The determinants will be after the midterm, probably. I think it's in chapter 3. But this is our first introduction to seeing a determinant in action. All right, some examples. All right, so let's say A equals 3, 4, 3, 4, 5, 6. Find A inverse if it exists. Right? So remember, for matrices, the inverse does not always exist. How do we know? We have to look at the determinant of the matrix. We want to double check, is the determinant 0 or not? We want it to be not 0. The determinant is, for a 2 by 2, AD minus BC. I'm multiplying the first column, or sorry, the first diagonal. I'm multiplying the first diagonal, which is 3 times 6. That's 18. Minus the off diagonal, 4 times 5 is 20. We get -2, which is great. All we needed was that AD minus BC is not 0. It could be any number. As long as it's not 0, we're golden. We can do this. All right, so how do we find A inverse? Well, according to our formula, A inverse is going to be 1 divided by the determinant times, now I want to flip the diagonal, the first diagonal, 6, 3, and I want to apply negatives to the off diagonal. -4, -5. And honestly, for a test or midterm, if you wrote just this and that's all you wrote, I would trying to multiply some weird fraction, get some decimals. So if you're doing this on a test and you stopped here, I would give this full credit, right? This is all I'm really looking for. Okay. But if I were to multiply it, then, okay, we would get 6 divided by 2, we're going to have a negative 3. Negative 4 divided by negative 2 will be a positive 2. Negative 5 divided by negative 2 will be 2.5. And yes, it's perfectly fine to have decimals in a matrix or fractions in a matrix. There's nothing wrong with that, right? A matrix is just some kind of array with rows and columns that is filled with real numbers. Those real numbers can be anything. In fact, those real numbers can be irrational. So you can even have pi in here if you want. There are some applications where having these irrational entries can like model either like growth modeling, if you're trying to model the growth of a population of deer, or growth of a population of wolves and deer in some national park, or maybe you're trying to model like the growth of bacteria in some kind of petri dish, or maybe you're trying to model the growth of a bank account given some savings, some kind of savings interest that you have with your bank, right? All these things are like growth or decay kind of models, and those things can be modeled with matrices. All right, side tangent. Let's finish the problem here. 3 divided by negative 2, negative 1.5. All right, great. So an inverse exists. Now that's all fine and good. Why do we care about finding an inverse matrix? Well, now that we have an inverse matrix, we can use this to solve matrix equation. 3 equals 3, 5x1 plus 6x2 equals 7. Well, this is the same thing as the matrix equation. 3, 4, 5, 6 times x equals 3, 7, right? This is my matrix A. This is B. If I multiply by A inverse on the left, well, A inverse times A is the identity matrix. In other words, my solution to this problem equals A inverse times B. Well, what's A inverse? We just found it above. Negative 3, 2, 2.5, negative 1.5 times B, which is 3, 7. And now, lo and behold, I can find x. What is x? Well, if you do your dot product here, you're going to get 5, negative 3. And I didn't have to do any row reduction to solve this problem. I found the inverse matrix, multiplied by A inverse, and then I can get my vector x. Does this answer work? We'll plug it in. It says x1 is 5, x2 is negative 3. All right, 3 times 5 is 15, plus 4 times negative 3 is negative 12. Well, 15 minus 12 is 3. So great, that works. And you can check it for the second equation. It's also a solution there. So this is one example for why we care about inverse matrices. As we continue in the summer, we're going to find out that inverse matrices have other special properties. There are other special things we can do with them. But this is a first case example of why we like inverse matrices. Okay. I want to show you some other properties of inverses. All right, what other properties do we have here? Well, first, I want to show you that if you take the inverse of an inverse matrix, that just gets you back to the matrix A, right? Why is this the case? Well, the inverse of a matrix is just supposed to be whatever matrix is going to make it happen, so that the matrix times this other one is going to give you the identity. Well, that means the inverse of an inverse is just the original A. Since those are the two matrices you can multiply by, they're going to flip things, right? You can think about with real numbers, 3 inverse is just 3, right? Same idea with matrices here. Okay. Now this next one is a little bit different. If you're trying to take the inverse of a matrix A times a matrix B, now of course these both have to be square, otherwise you couldn't take an inverse, right? They have to be square. This is going to be, you're going to flip the order, and it's going to be B inverse times A inverse, right? This is really key here because recall for matrices, you cannot just flip the order whenever you like. There are only certain occasions when flipping an order can work. So this does not equal A inverse times B inverse, right? The inverse of a matrix times a matrix, it doesn't work like real numbers. You can't just distribute this power or anything. This is not equal to A inverse B inverse. Why? Well, think about it. In order for an inverse to work, in order to be an inverse, that means AB times AB inverse is supposed to equal the identity matrix, right? This is a fact we already know. Well, if the inverse of A times B was A inverse B inverse of matrix A times matrix B. In fact, for this specific equation I've written out here, there's nothing I can do to simplify this because with matrices, I cannot flip the order of multiplication. So this can't simplify, meaning this does not equal the identity. So A inverse B inverse does not work. But if AB inverse is B inverse A inverse, well, now what happens? Well, now it works all nice. B times B inverse is the identity. So this is A times the identity times A inverse. But that's really just A times A inverse. But now that's just the identity, right? So when you're trying to take the inverse of things being multiplied, it reverses the order of what you see on the inside, and you're taking the inverse of each piece. All right, so you want to be very careful about this fact. This is going to be more important in later in chapter 2 as well. All right, great. We also have that since we're talking about square matrices, remember what is the transpose? We're swapping rows and columns. And if you swap rows and columns, it's not going to hurt anything. You can still find an inverse, right? So A invertible means that its transpose is also invertible. And in fact, we have this nice property where if you take the inverse of the transpose, if you take the inverse of a transpose, that's the same thing as taking the transpose of the inverse. Why? Well, remember, transpose rows and columns, everything else is going to be preserved. The order of the rows and columns is preserved. So all those other properties, that formula we had above, it all still works out. And so we have this nice thing happen for transposes. Okay, great. Let's see. Trying to wrap things up. There are two other things I want to talk about real quick. So first, based on everything we've said, we can now write another theorem. All right. So this theorem is also going to be really handy for telling when a matrix is invertible or not. Let A be an n by n matrix. Okay. then we're going to say A is invertible if and only if A is row equivalent to the identity matrix for an n by n. In other words, if you're row equivalent to the identity matrix, you have a pivot in every column. Or in other words, this is the same thing as saying A is linearly independent, which is the same thing as saying A has a pivot in every column. If A does not have a pivot in every column, it is not invertible, right? So that's just another way you can tell if something is invertible or not. Why is this true? Why does this theorem work, right? This if and only if this goes both directions, which means this implies all of that, and all of this implies A invertible. Why? Well, for left implies right, think about if A is invertible, that means AX equals B has a solution. X just equals A inverse times B. But that means we have a solution for every single B, right? We have a solution for every B. Well, if we have a solution for every B, that means we are onto, which means I have a pivot in every row. I have n pivots. But if I have n pivots, that means I also have a pivot in every column. This is something special about square matrices. Onto and one-to-one are equivalent properties when it's square. Why? Well, if it's square like a 2x2 and you have a pivot in every row, that means you have two pivots. That means you also have a pivot in every column, right? And vice versa. So the fact that we have a solution for every possible B tells us that A has a pivot in every column, it has a pivot in every row, it's linearly independent, it's row equivalent to the identity, okay? How can we go in the reverse direction? Well, in the reverse direction, why does the right side imply the left? If A is row equivalent to the identity, then that means there is a way to reduce A to the identity matrix. There are row operations. Which means there are reverse row operations, right? This means there are reverse row operations to go from the identity to A. Well, these reverse operations, that's exactly what the matrix A inverse is. The reverse row operations is what undoes a matrix multiplication, right? When we have A inverse times A times X, recall, A inverse times A times X is just X. When multiplied by an inverse matrix, it's undoing this linear combination. It's undoing the row operations that are happening here. So if you can reduce A to the identity, there are also reverse row operations exist. And if reverse row operations exist, that means A inverse exists. So it's invertible. So this leads us to another methodology for finding an inverse matrix. We can also find an inverse matrix by just keeping track of what are the reverse operations, right? And in fact, this is one method for finding the inverse of matrices which are bigger than a 2x2. You can do this to find the inverse of a 3x3 or 4x4, so on and so forth. How can we do that? Well, let me show you real quick, and then we'll do today's participation question. So final example for today. Let's suppose A is this matrix 0, 1, 2, 1, 0, 3, 4, negative 3, 8, right? How can we find A inverse? Well, we've just said that if we can keep track of the operations that result in the identity and look at the reverse operations, that is going to give us the inverse matrix, right? So in other words, okay, I'm going to take my matrix A, 0, 1, 2, 1, 0, 3, 4, negative 3, 8. And I'm going to put this vertical bar here. And on the other side, I'm going to put the identity matrix. And basically, what I'm going to do is I'm going to change this left side into the identity matrix, right? I want to change the left side to make it look like the identity. Well, in that case, I need to start by getting a pivot in the top left. I need to swap row 1 and row 2. So swap, but I'm swapping the entire row on the right side. Now, what am I highlighting here? Well, what's nice about this method is that while I'm changing the left to look like the identity matrix, this right side is keeping track of what operations I've performed. The right side, I flipped the rows, right? This is keeping track of what's happening to the identity matrix. In fact, as I change the left into the identity, because it's doing the same operations, we're doing this reverse order, the identity on the right side is going to turn into A inverse. So in other words, just for the sake of time, I'm not going to show all the steps, but you can continue for practice. If you take A and you put the identity on the other side, and you row reduce this so that you have the identity on the left, well, then your inverse will be on the right side, right? Because this is keeping track of the reverse operations. So if you continue doing the row reduction here to turn the left into the identity, I'm going to skip over some steps. If you look in Canvas in section 2.2 lecture notes, I show all of these steps, step by step, so you can look at it. But if you continue row reducing, well, then eventually on the left, you get the identity. And then on the right side, we're going to have negative 4.5, 7, negative 1.5, negative 2, 4, negative 1, 1.5, negative 2, 0.5, right? We found the inverse matrix. When you're looking at matrices bigger than a 2 by, yes, it can. But as we continue in the class, we're going to see that, well, even if it is messy, the inverse matrix is going to be handy in a lot of different situations. Okay, great. Enough of that. Let's look at today's participation question. This is participation day 9, I believe. Let me double check. Participation day 9. Yes, great. So if you look at participation day 9, I'll share my screen. All right, sharing my screen. Participation day 9. Given the matrix A, is the matrix invertible? If so, find the inverse. What's the first thing we have to check? We want to know, is the determinant non-zero? It has to be non-zero to find an inverse. If it is 0, there's no inverse. Okay, so what is our determinant? Remember, the determinant for a 2 by 2 is multiply the diagonal, that's 36, minus multiply the off diagonal. Well, 6 times 6 is 36, minus negative 4 times negative 9 will be a positive 36. We have 36 minus 36. In other words, our determinant for this matrix is 0. Well, what does that mean? Because the determinant is 0, that means an inverse does not exist. So given the matrix A, is the matrix invertible? No. No, A is not invertible. Why? Because the determinant is 0. That's why. So the inverse does not exist. A is not invertible. And that's it for today's participation question. All right, everybody. I know I went a little bit longer than usual. Most of the videos tend. Otherwise, if you have questions, please feel free to email me. Office hours are Tuesday and Thursday, so there's an office hour tomorrow as well. Otherwise, that's all for today. Best of luck, and I'll see you tomorrow.